Okay, so flux correction and climate models. From my experience, I've been working with this a lot since my PhD, that there's a lot of negative attitude towards flux correction. It sounds like it's the worst thing you can possibly do. And I think this is misleading. It's actually a really good tool. And I want to give a little bit of an introduction to this. So I will show you a little bit further about what does it mean, flux correction as a method, and then I give you some historical overview and some examples in the literature. Then why should you use it? And then actually, and I give you a recent example which I use to increase ENSO performance in the ICON model. Okay, first about the method. So what is flux correction? So I give you an example because there's many different ways of how this is being used, but a very common one is this example. So let's say the assumption is that your mean state SST is causing biases in your feedbacks. Let's say in INYO or so, the feedbacks are wrong. And partly this might be due to the mean state or SST gradients being incorrect. So what you can do in a covered model is you can force your mean SST to look like whatever you want it to look like, say like observations. And you can achieve this by additionally adding some artificial net heat flux into your ocean. So that's the approach to fix your mean state in a covered model, and that is called flux correction. So in terms of equations, this would look like this. Let's say we have an SST surface temperature tendency equation with a heat capacity, and then the tendencies and SST. They are different at each location, and they are a function of time. And in principle, they have some atmospheric forcing at each location at each time, and then they have an oceanic forcing at each location at each time. And we are adding an artificial term, which we call a Q flux or a heat flux, that is a function of location, but it's not a function of time. It's a function of calendar year time. So what time of the year are we? And if we are at a certain time of the year, you put a certain amount of heat flux into the tendency equation of your SST. So this is important. So this is not a function of the current time. It's just a function of the calendar date in the year. So a few things about this flux. So you have a mean heat flux that leads to a correct SST climatology. So the SST climatology that you want to have. So whatever SST climatology you want to have, you can force your model to have this by choosing the right kind of Q flux. This is not state dependent. So as I said, this is here, this T is not the real time. It's just the time of the year. So depending on what state your model is, whether it's drifting 10 degrees up or 10 degrees down or whatever, you will always put the same flux in it, which is different from these other terms. All these other terms will be state dependent, but this term is not state dependent. So therefore, it's not a direct feedback. So there are other methods like nudging or where people play around with parameters and processes. These will all be directly affecting feedbacks, but flux correction is not a feedback thing. It does not directly affect feedbacks. It does it indirectly by having a different mean state at the end, and this affects then the other feedbacks. But it's in itself, it has no feedbacks. It's just an arbitrary flux. You can imagine it as some kind of incoming sunlight or incoming absorbed sunlight at a wavelength that has where the albedo is always black, right? So it's always absorbed. You can estimate this by different ways. Typically, people do a nudging run and then write out the fluxes, or the way that I do it, I do an iteration. I run the model, see how much it's incorrect, and then I estimate how much watts per square meter would I need to correct it, and then I do it several times, typically about 4 to 5 times. It's typically defined on a monthly climatology, so you have a different map of correction fluxes at each calendar month, and then you interpolate between calendar days in a linear way. Flux corrections is also used in many other situations, not just sea surface temperatures. So this is used in 3D atmospheric temperatures, atmospheric moistures, and atmospheric winds. It is used to correct the wind stress. It is used to correct land surface temperatures. It is used to correct ocean salinities and many other things. So there's many different ways of how you can correct your model to have a desired or realistic mean state in some variables, and then hopefully this will actually improve your dynamics. Okay, I'll give you a little bit of an overview of some examples of how this has been applied recently, and then also a little bit of the background. So historically, I think in the first generation of GCMs didn't really have an ocean GCM. So they had an atmospheric model, and then they had an ocean boundary condition, which was a slab ocean or just SSTs. And since the slab ocean would not have any kind of meridional heat transport or boundary currents that are important for the mean SST, they use flux corrections to make the mean SST look more realistic. And they're still being used. If you use a slab ocean model, typically people still use flux corrections to make the slab ocean model look more like the real world. And I think then later on in the 1990s or so, people avoided this. So they basically said the models are good enough to run without these artificial corrections. I'm not exactly sure when this happened. Maybe in CMIP3, most of the models or all of the models had no flux correction terms in it. Whether this is a good idea or not, I would question that this is a good idea. I think they probably should have still used flux corrections, but they don't use it anymore. But in other covered model simulations, not CMIP, but other situations like seasonal forecasting or so, people use it. And I will show you some examples of this. Okay, so some examples from the literature, and I focus on a few things that are more recent, but I think there are many examples. So this is one here from the GFDL group, Veggie et al. And this is about tropical cyclones. So they have used a covered model to predict seasonal prediction of tropical cyclones. And they notice that their model is not really good in many of the statistics. So here you see statistics of number of tropical cyclones per day, days per season. The upper one is observed, and the middle one is their model without any corrections. And you can see, for example, if you look at the Atlantic near the US, the numbers are way too small in the model, and in the observations, this should be much larger. And also in the Pacific, the numbers are off. And then they do flux corrections of the SST, just as I described it. And then you can see that the distribution of number of tropical cyclone days is more realistic than in the uncorrected model, because the sea surface temperatures are just more realistic and the sea surface temperature bias are disappeared. And that makes the distribution of tropical cyclones to be more realistic. So they basically conclude in this study from 2014 that this is helpful, that this makes the model improve. And they show a number of other statistics that all kind of seem to suggest that the model performs better in tropical cyclone activities when you have the SST flux corrected to look more like the real world. And this is a very typical, I think, kind of application that people have done many times in the past in seasonal forecasting, that they use this to make better seasonal forecasting. And it works in many ways. I'm not sure whether it always works. There are probably things where it didn't, but the examples that I know of, it typically makes the model behave better. Here's another example. This is about the warming trend in the tropical Pacific. You probably heard about this. So in the observed here, there's a little bit of a La Nina-like warming trend. So in the East Equatorial Pacific, there's less warming, and in the Western Equatorial Pacific, there's more warming. And if you look at the CMIP6 models, they all predict that the East should warm more than the West. So there's a clear mismatch between what should happen, what the models predict, and what actually did happen over the last 40 years. And in this study, they used the ESM model, which is here on the left, and then they corrected with flux correction to have the SST look like more like the real world. And then they look at these two trends. They actually look fairly similar, but if you make the difference plot between these two trends, you see this here. That means the flux corrected one has more of a less warming in the East and more warming in the West, like it's observed. So they are kind of suggesting that the models behave more realistic or more like observed if you are flux correcting the sea surface temperatures. I mean, the model is still somewhat off. The trend doesn't really look like observed in all details, but it's more realistic than the observed one, than the previous one without flux correction. So this is a study from last year. So you can see that there's a bunch of group topics where this method is used, and they think it's helpful to improve the performance of the models. And now I'll give you some examples from my own research, because I've been basically using flux corrections since my PhD, so for the last 30 years almost. So here's a study where I kind of try to figure out whether the mean as a sea surface temperatures matter in terms of making the correct climate change projections. So I'm arguing here that the biases that the models have in the mean sea surface temperatures affect the global warming response. And what I show you here on the left is basically response experiments with 2 times CO2. So you see here an ensemble of atmosphere model with a slab ocean. And I run a control run, and I run an ensemble of control runs, and you see there's a little bit of variations in the global mean temperatures, but not much. And then I do a double CO2, and you can see the double CO2 has a little bit of variations in these 5 ensemble members, but not much. So this is a run where we have an atmosphere, and the slab ocean has a climatology that is identical to the CMIP3 mean climatology, which is different from observed. They have common biases. And then I redo this many times. And each of this run now is the same model, but I force each ensemble member to have a different SST climatology from the CMIP3 ensemble. So there are about 20 or 30 CMIP3 members. Each of them has a different SST climatology. I force my model to have this different SST climatology and then rerun this experiment. And you can see in the control, the variations is not much stronger than in this one here. So they are about similar. But in the CO2 response experiments, there's a much bigger ensemble spread than in this run where all the ensemble members have the same SST climatology. So I'm arguing here that different SST climatologies will lead to different CO2 responses. So that this mean state biases in the models and the SST has a substantial impact on uncertainty in the as a CO2 response. And of course, I'm achieving this by this flux correction approach to get all of these models into these different SST climatologies. So that's the study. It's a bit older, from 2012, but that's what I've done. Okay, here's another example that's a bit more complicated. This is about a few years ago, 2018, and I used a simple model. This is not a GCM. This is a globally resolved energy balance model. It's very simple. It runs 100,000 years on my laptop in a day, so it's a very different kind of model. But I'm asking the question about how do you develop covered models, whether you should be tuning or flux correcting. So I'm trying to confront whether tuning parameters is better or whether flux correction is better. Okay, and it takes a little bit to explain this. So in the left column here, I'm tuning. And what I'm doing is I'm doing a perfect model approach. So I assume I have a model which I consider the real world. And then I create 21 different models. They are basically having different parameters. So they have 21 parameters that I perturb. I pick one of them to be as a real world. And then the other ones, the perturbed ones, are different models. And then I pick 5 of these parameters and try to optimize them to get the original. So I have an optimization scheme where I try to tune the parameters to get back to the original and see whether my model would perform better. So the first map that I show you here is the improvement in the control run, so the pre-industrial run basically. And this bluish color means a reduction of biases by about 80 to 100%. So it means I can actually, by tuning these 5 parameters, I can actually make these control mean state biases almost disappear. So there are some regions here in Central Asia where it doesn't work as well, but for most of the regions it's bluish. That means it's more than 80% reduction in the control mean state climate can be reduced by tuning the parameters. So that sounds, first of all, as a success. Then I do a CO2 response experiment and I see how much does the CO2 response change and how much did I get closer to the original, the true SST response to double of CO2. And then you can see there's also greenish and bluish color mostly. That means the uncertainty do reduce in the response as well. So in other words, that says basically that the tuning works. You're improving your mean state. You make the model behave better in the control run, and it will also behave better in the CO2 run, even though this wasn't part of my tuning. This is basically a test of whether this method works or not. And you can see for most regions, it is greenish and bluish, so that actually does improve the model. But then there's this tropical region here where this model actually doesn't have much of a CO2 response, but the response gets worse. So that means the errors increase by improving the parameters. But a big caveat from the tuning here is that if you look at the distance of your tuned parameter to the actually true parameters, so I start out with 100% error, and then I tune the parameters, and you can see I've did this many times, the errors increase. And actually, the parameters that I'm optimizing drift away from the original ones, but the model behaves better. So it's kind of a mixed outcome. If I reproduce the same thing with flux corrections, so first with flux corrections, I can get rid of all the errors in the control one. So the model will look perfect. But then if I test this in the response, you can see it's also greenish and bluish in most regions. So it improves the response to CO2, but not in the tropics, actually makes it worse. So you can see that the flux corrections, in some sense, it suggests to you an almost perfect model in the control one. But actually, some of the responses in the tropics here get actually worse. But then in most regions, and from where the responses are strongest in the higher latitudes, the response biases actually do get reduced. So it's a bit of a mixed bag. So you can see tuning is not perfect, flux correction is not perfect, but actually flux corrections performs a little bit better than the tuning, but neither of them is perfect. Okay, so why would I use flux corrections? So I give you a little bit of a background, but you can already see of where this is going. So I think the argument for flux corrections is that simply your model performs better. There's no other argument. It's whatever you apply it for and you can test it for, the model will usually perform better if you flux correct it. And that is because that many of the processes and feedbacks that you are interested are mean state dependent. And if you are operating your covered model at a correct mean state, it is likely to perform better. But there's no guarantee. And I just showed you that there are some situations like the tropics in my simple model that behave worse. So there's no guarantee for this, but in general, it will likely perform better. Or to formulate it differently, the alternative performs worse. That is, if you do artificial tuning, and all models do this, there's not a published CMIP model that doesn't do it. So every CMIP model is artificially tuned. That will typically perform worse. Right? So that's probably the argument of why you should use flux correction, because it actually performs better. Another argument I think which is important is that artificial tuning is really messy. If you think about the tuning process that every group, ACCESS, MPI in Germany, or any other group does, this tuning process is really, really messy. First of all, it's really expensive. You have to run your model many, many, many times. So probably 1,000 times. Then what you do with your parameters is really intransparent. You don't know what exactly each of these parameters are. They all have different units. The impact on the climate is very complicated. It's not easy to measure. Unlike flux corrections, which is given in watts per square meter, you immediately know what it means, more or less. And typically also this tuning is quite often undocumented. You do not really know what all the parameters, what elements of them are artificial and what elements are actually truly based on observations. And it's highly ineffective, I think. So this is an argument I think is against artificial tuning. Nevertheless, everybody does this, and I'm not saying you should not do it. You probably have to do it to some degree. But compared to flux corrections, flux correction is way easier and it's much more effective, but it's not perfect. Okay, I give you an example of what I've been working on in the last few months. That is trying to improve the ENSO performance of the icon model from the MPI. I think I talked about this before last year. So I'm involved in the icon XPP development. They developed this for seasonal forecasting and for CMIP 7. And they asked me to look at ENSO and think of ways of improving it. And I suggested to them, okay, we can improve ENSO to flux corrections, and they don't want this. I showed them what I'm showing you now. They are quite impressed by how much it gets better, but they still don't want to use flux corrections. But anyway, I'm still working on to convince them that they actually should use flux corrections. So this model that I'm talking about has 160 degrees, 160 kilometers atmosphere, 40 kilometers ocean resolution. It is this kind of irregular grid. You see these little triangles in the oceans. So they are just indicating what it looks like. So there's higher resolutions at some points, like here in the North Atlantic, and then lower resolutions in the South Atlantic. So the grid is irregular. So the model is really fast on the German computer. It runs about 80 years a day. And this is why I can actually really do lots of runs. So in the last 2 years, we probably did about 1,000 runs of about 5 to 50 years. So we did many, many runs. And then the higher resolution version that is aimed for CMAP7 is then twice the resolution, so 80 kilometers in the atmosphere and 20 kilometers in the ocean. To show you what this model looks like, so the upper plot is the mean sea surface temperature observed. The left is the model that I started with. So that is the model without flux corrections, and that is the control run that I'm working with. And you can see the SST has a very strong cold tongue bias. So here's the bias map. It's way too cold along the equator. It's too cold in the North Pacific. Typically too warm here in the upwelling regions around South America. Same with the Atlantic region of Africa. It's way too warm. So it has substantial biases, and the bias is on the order of 2 degrees. And then in the upwelling region, it's more than 2 degrees. And then when I flux correct it, so biases basically disappear. And you can see the SST map looks more or less like the observed one. It's not perfect. There are still about half a degree or less biases, but you can clearly see the biases are much smaller. So the heat flux that I have to put in to correct this bias looks like this here. So the heat fluxes here are up to, in this central equatorial Pacific, they are up to 80 watts per square meters. So these are substantial heat fluxes. If you look at the heat flux correction map compared to the SST bias map, you would say they're exactly matching, but they are not exactly matching. If you look, for example, in the Indian Ocean, all of the Indian Ocean is too cold, and then the heat flux is actually cooling further. This sounds a bit strange, but the problem is that these biases are not due to local errors. So this bias in the Indian Ocean being too cold, it's actually a combination of biases in the Indian Ocean and biases in the Pacific. So if I have a too cold Pacific and I warm it up here, then the warming of the Pacific will also warm up the Indian Ocean. This is why I have to then compensate it with cooling. Similar things happens in the Atlantic. So these interactions are not local, they are global interactions. But to first order, you can see the heat flux that I put in is roughly the opposite of my bias, but not perfectly the opposite. You can also see here in the equatorial Pacific, the heating here is a little bit further to the east than where the actually cold anomaly is, because the easterly wind will just transport the heat to the west and then cool it further to the west. I'm also correcting wind stress. So what I do, if you look at the wind stress, the upper one is observed, and the right one here is the seasonal cycle. The model looks actually pretty good in the wind stress, but you can also see in the Indian Ocean here, the wind stress is a little bit too strong compared to observed. And the difference map between these two, I actually just add when I transfer the wind stress to the ocean and the coupling. This additional wind stress map down here is added to the one that the atmosphere produces. So then the ocean sees a more or less exactly mean wind stress as it is observed. Okay, what does this do? So I have the Plankton et al. Ensor matrix, which I use to evaluate whether my model is better or worse. And they basically have they have 20 something indices. Some are about variability and some about processes and some about other things that I ignore for now. So I only look at variability and processes. And I put them all together here in these normalized mean biases that Plankton et al. Defines. So normalized means that 0 means it's the average bias of the CMAP5 and CMAP6 models. And the gray distribution here is the distribution of all the CMAP5 and CMAP6 models that Plankton et al. Have published in the BAMS article. So you can see they have a spread, and the better ones are to the left. So less bias, so negative numbers means good, and positive numbers means bad. As a reference, I have ERA reanalysis here. So it's basically what you can assume as perfect. This is this similar as this light blue line here. So this is where you want to be. And you can see the models are fairly far away from this. Some models are pretty far away, and then some models are closer. So the run that I started with is the black line. So this is the model without any corrections. And the blue line is the one with flux corrections. So you can see the flux corrected model behaves much better, both in terms of variability, which is down here on the left, and in terms of processes. They are way better than the initial model that I started with. So the initial model that I started with was kind of average, CMAP5, CMAP6. And now the flux corrected one is basically as good as the best model. I put in here the numbers of the best model. It's a minus 0.9. and the flux corrected one is minus 1.0. So it's better than the best model in the archive from Planton et al. Just by putting in flux corrections. I have another run where I also tune the parameters. So in addition to the flux corrections, I also tune some parameters, and then that makes it even better a little bit. So I show you a few ENSO statistics to show you what this looks like. So first of all, this is about the mean climate. So here, first of all, is the equatorial mean SST. So black is observed. And my flux corrected run is pretty close to observed. It's not perfect, but pretty close. And the blue one is the one that I started with without corrections. And you can see it has a very strong core-tongue bias. So zonal, equatorial mean zonal wind stress, they both have biases. So the blue one is the without flux correction. And then with the flux corrections, the winds substantially change, they shift to the east and become stronger. So both of them are not perfect, but you can clearly see that the winds have changed. The two lower plots about precipitation. So first of all, here's a zonal mean precipitation that shows you a little bit the southern hemisphere and northern hemisphere. So the model has the typical double ITZ problem, the blue curve, but the double ITZ problem is strongly reduced if you flux correct. But it rains too much in this model. And then along the equator, you can see the model was not raining enough along the equator because it was simply too cold. But now it rains too much along the equator. But it's probably more realistic. More interesting is the ENSO variability. So the upper left is the SST standard deviation along the equator. So you can see here the black curve is that the standard deviation is low in the west and then high in the east. And the initial model was fairly weak all around. And now the new flux corrected model is actually a bit too strong. In terms of ENSO pattern, so this is kind of looking at the ENSO pattern along the equator. So the ENSO pattern along the equator should have a large amplitude in the east. Somebody had a question or no?
I think this is a glitch. Go for it.
Yeah. So the amplitude should be large in the east and then transition to negative in the west or to zero. And the control model was basically also peaking in the east, but it has way too much amplitude in the west, which is typical what most CMIP models have, that they have ENSO variability to be too strong in the west. And the flux corrected model looks much more realistic in this sense. Then the seasonal cycle, so ENSO variability should be weakest in around April and strongest around December. That is observed. And the control one didn't really have a clear seasonal cycle, but the new one actually has a much better seasonal cycle. Probably one of the nicest things is the nonlinearity, so the SST skewness. So in the real world, the skewness is positive in the east. That means more extreme positive values El Niños. And in the west, it should be negative skewness, so more extreme La Niñas. And the control model didn't have any of that. So it has basically no skewness. But the flux corrected model has almost realistic as observed skewness. It has very strong skewness in the west, in the east, that is positive, and it has negative skewness in the east. So that looks actually really realistic. And this is now about processes. So this is mostly about the Bjerknes feedbacks and the net heat flux feedback. So I look at basically regressions here. This is a regression between wind stress and SST. That should be fairly strong in the center to west Pacific. And the control one was way too weak and displaced, and the flux corrected one is way better. And the sea surface height, which is a measure of heat content or the structure of the upper ocean, sends a regression to wind stress. This is also much better now in this model compared to the control one. And then the last element of the Bjerknes feedback is how the SST responds to sea surface heights. It's not quite clear. I think they are about similar. And then the other one is the net heat flux and negative feedback between atmospheric heat flux and SST. That needs to be strongly negative, so about 20 watts per square meter per Kelvin negative. And in the control one, this was much too weak. There was not much of a negative feedback, but this is now much stronger in the flux corrected run. Okay, I think what I've shown you in summary, so first of all, in summary of this ICO model, it's way better when it's flux corrected. This is actually surprisingly improved, more than I expected initially, but because people have done this in the past with other models and they saw just small improvements. But this here is now a very substantial improvement in the performance by just flux correcting. So in summary, flux corrections are used in many different ways in cupboard model simulations. And they can improve the performance, but there's no guarantee that they does, but quite often they do. The icon model and the performance has greatly improved by flux correction, mostly due to the heat flux, but also due to the wind stress corrections. And I think that flux correction is clearly and better, or can be a better alternative than tuning the models. I'm not saying you should not tune the models, but I'm saying that in many ways you might be better off of using flux corrections. All right, that's all.